Hi, Chase.
Hello?
How are you today?
I'm doing pretty good.
Okay.
It's been a good week.
It's been a good week.
Yeah.
Are you a Bronco fan at all?
No, but my birthday was yesterday, so it was hard to be a bad week.
Okay.
I'm not a big fan of sports.
No, I know. Although I have to admit that it almost goes beyond sports when a team is in the Super Bowl. The city goes a little bit nuts. So, all right. I looked at these three documents that you emailed to me. Chapters 4.2, 4.3, and a little bit of 4.4. Now, we talked a lot last week about area under the curve and how to get it using left, right, and mid rectangle. Well, this chapter, the difficult part of this chapter, and in fact one of the most difficult parts of integral calculus, is this concept of the limit definition of, in other words, the area under the curve is equal to the limit as n goes to infinity of sigma I going from 1 to n of f of c sub I delta x. Well, this thing's just about the most complicated thing in the world. The best way for me to try to explain this is if you think back to differential calculus. Remember when we first figured out the limit of derivative? And the definition for the limit of the derivative was the limit as h went to 0 of f of x plus h minus f of x all over h. This is the official definition of first derivative. Well, this is the official definition of integral, or area under the curve. If you remember back with differential calculus, this was unbelievably difficult to do.
Yeah.
But once we learned the power rule, the product rule, the quotient rule, and the chain rule, these things became far easier. It was much easier to take the derivative using the power rule than it was by the limit definition. This is called the limit quotient definition of derivative. Well, we're faced with the same thing, and I actually disagree quite a bit with teaching calculus this way. I think it's better if you talk about area under the curve and you immediately go into the integral, which is the antiderivative, and it's very understandable, very easy. This limit definition for area under the curve is not easily understood. It's tough. I rarely have to teach anybody this. You're probably the second person in 5 years that gets this much. I mean, this is the second session in a row where we've had to deal with the limit definition of area under the curve. And last week I just kind of put it off because I prefer starting with easy stuff and then going to medium stuff and so forth, and we didn't get to it. But you're still on it. So let's talk about how we use it. I'm going to guess that this gave you more trouble than anything else on this material.
Yeah, that it looks basically,
Okay.
very confusing.
Me too, to be honest. And in fact, I spent a couple hours this morning trying to do 1 and 2, and I couldn't come up with an answer that agreed with them. And of course, I know what the answer is because there's an easy way to do 1 and 2. In other words, the easy way is to take the integral of that function and evaluate it. If I want to know what the area under the curve from 1 to 2 of x squared is, well, I use the reverse power rule, and I evaluate it from 1 to 2. So that becomes 8/3 minus 1/3, or 7/3, piece of cake. But to do it by this method is very difficult. So here's what I'm going to suggest, is that we start with number 5. I assume that your homework assignment is to do all these odd ones?
This is which one? The 4.3 document?
Yeah.
4.3, it was, yeah, I'll just, those ones.
Oh, really?
Yeah.
Ah, very interesting. Very interesting. In other words, they are not focusing on 1 through 8.
The journal question for this week is focused on the concept of 1 through 8.
In other words, this homework here, where we have to do 1 and 2?
Yeah.
All right. Let's leave those till the end. If we have time, we will address them. And I'm certainly willing to talk about them. But I have a little bit of confusion about them myself. And I'm reluctant to try to tutor you on something that I'm not 100% sure of. So, let's look at your homework.
Okay.
9. And the instructions here say, write the limit as a definite integral on the interval a to b where c is any point in the ith sum interval. Well, these are a piece of cake. Number 9, what is that going to be?
So for number 9 might be, so we're integrating the 3c plus 10, right?
Mm-hmm.
So we get,
I want to translate this expression that they've given me into a definite integral with the integral sign, with a lower limit of integration, with an upper limit of integration, and a function.
so the lower limit of integration would be -1, right?
Uh-huh.
And if the upper limit is -5,
Positive 5.
oh, sorry, yeah, +5. And then
We know that the delta x is going to translate into a dx,
yeah,
which means we have to have a function of x. If I put a function of y in here, I can't integrate it. I can only integrate it if it's a function of x. What do you suppose that function of x is?
3x plus 10.
That's it. And it's as easy as that. In other words, every one of these problems here, you're going to substitute x for c, and the limits of integration will be over here on this interval.
Okay.
Okay? So 9 is particularly easy. 17, let's look at 17. 17 set up a definite integral that yields the area of the region. Do not evaluate the integral. how are we going to figure out the area under this curve with a definite integral?
Would we take the minimum and maximum as where it touches the x-axis?
You got
and
it.
Then
minus 5 to 5.
5.
Of
And
the
then,
function, whatever this function is, I'm going to do f of x dx. Well, this function happens to be 25 minus x squared. Now, let's just make sure you know how you would solve this. Even though it might be getting a little ahead, I think you know how to do this. What's the equal to?
look, you solve it.
First of all, it's equal to this.
Yeah.
In other words, when you're subtracting, you can separate it into two integrals. When you're adding, you can separate it into integrals. Multiplying and dividing, different story. So what's the integral of that?
We would have just 25x, but then do we...
Evaluated between minus 5 and 5. Minus, what's the integral of x squared?
X to the x cubed over 3.
Evaluated from minus 5 to 5. And that's the way we're going to solve that. In other words, this one here is 125 minus a minus 125. This one over here is, and if you don't understand these numbers, holler. I'm going to assume that if you don't say anything, you understand how I got them. And this is 125 thirds minus a minus 125 thirds. So this whole thing becomes 250 minus the quantity 250 thirds. In other words, what's inside here is 250 thirds. So this is 750 thirds minus 250 thirds. 500 thirds is the answer for that one. Now, I know they didn't ask for that, and that's fine. But if you didn't know how to do it, you need to know how to do it. Okay? Any questions on that one?
No, that makes sense.
Okay.
Well, yeah. I wasn't sure on how you evaluated it, but yeah, it makes sense what you showed.
Okay. Yeah, evaluating so far, the only method you have for doing antiderivatives is the reverse power rule, correct?
Yes.
In other words, you can, or a trig function. You know how to do that also. But you know how to integrate x to the third or x to the 1/2, any of that. If I said integrate x times sine x, that'd be a different story. But at this point, you should know how to integrate all of these just by the power rule. 18 might be a little different. That's a little harder to integrate, but we don't want to talk about that right now. 19. Hold on a second. Let me get my... What's the area under that curve?
19, yeah, under cosine x. So, we're writing this like we wrote the last one, right?
Uh-huh. Yeah, using integrals. Not sigma, but integrals. Sigma is the hard way to do all of it. Absolutely the hardest way to do integrals is the sigma notation. Why they start out with that, I don't know.
seem to always start out with the hardest way to do
Well, there's definitely some rhyme or reason to your homework assignment here. Notice that 1 through 8 was not in there. Good.
Yeah.
It shouldn't be in there. So, what's the area under this curve?
So it would be, we'd integrate cosine x, but I'm not sure what the minimum and maximum would be.
It's always this point to this point on the x-axis.
So we would have 0 to pi over 2?
Uh-huh. Exactly that. And of course, the integral of cosine is sine. So I'm going to evaluate sine from 0 to pi over 2. Sine of pi over 2 is 1. Sine of 0 is 0. The area under that curve is 1. Okay?
Okay.
Now, I know 21 is on the list. Good, because I wanted to do, 19 wasn't on the list. Sorry. I meant 21, but I'm glad 21 is on the list. Because first of all, it's a little different. They don't want the area under the curve, do they?
They want the area above the curve.
Yeah. Well, we have g of y equals y cubed. So I could say x equals y cubed defines that line. Furthermore, I could say y equals the cube root of x. These are the same. Okay? So I have a couple of ways I can do this. I can figure up the area of this rectangle. 2 by 8, 16 is the area of that rectangle. And subtract out the area under the curve, which would be merely the integral of x to the 1/3 dx going from 0 to 8. So the answer would be 16 minus that. Now, first of all, do you understand that method?
Yeah,
In other words, this expression right here is going to give me this area right here, the white area under the curve.
it's
Well,
just like some of the more advanced
yeah, the
geometry
rectangle minus the white area is equal to this pink area here. Well, the rectangle is 16, so minus that's going to give me that. This is very straightforward. Do you know how to evaluate that?
So the 0 obviously would just, turns into a 0, right? So you just evaluate it at 8?
Yeah, well, yes, you can't always assume that the 0 turns into a 0, but in this case it does. But what's the integral of x to the 1/3?
X to the 1/3.
Add 1. First step is add 1.
It's 4/3 over x to the 3/4, yeah.
In other words, it's the new exponent. You divide by the new exponent, which is the same as multiplying by the inverse of that new exponent. Okay? And then I'm going to evaluate that from 0 to 8. And you're correct that when I put 0 in, this whole thing is 0. So the only thing I need to worry about is 8. Well, the cube root of 8 is 2. 2 to the 4th power is 16. I'm taking 3/4 of 16. This whole thing is 12. 16 minus 12. There's the area. Right there. 1/4 of that rectangle is occupied by that. Now, let's do it a different way. You understand that way perfectly?
Yes.
Okay, when you're doing area under the curve, you don't have to necessarily put your rectangles in a vertical motion. You can put them in a horizontal motion. In other words, if I want to look at this curve and find this area, I can make my rectangles horizontal like that and do it directly. And then I'm going to integrate on the y-axis because my skinny measurement is dy, not dx. So if I wanted to integrate this, I'm going to integrate with respect to y, which means I need a function of y. Well, that's nice. That's what they gave me. They gave it to me as a function of y. And I integrate from the bottom to the top, which in this case is from 0 to 2. In other words, that should give me the same area. What was our area the other way? 4?
Yes.
Okay. First of all, do you understand this conceptually?
Yeah.
In other words,
Yeah.
if I integrate on the y-axis, then I'm going to get the area between the y-axis and the curve, which is that pink area. That's what I want. I don't have to do this, find the area of the rectangle and subtract out the area of the white area. All I have to do is figure out the area between this line and the y-axis. And I do that by integrating along y. And if I'm going to integrate along y, I need a function that's in y. Well, this is in y. In other words, I can say this is x equals y cubed. So evaluating this gives me y to the 4th over 4, evaluated from 0 to 2. You go from bottom to top when you're integrating along y, just like you go from left to right if you're integrating along x. Well, what is this? This is 2 to the 4th, which is 16, divided by 4 minus 0. That's also equal to 4. But it's more direct.
Yeah.
And it's much easier. So that's usually the reason we integrate along the y-axis, is because it's easier. Or sometimes, in this case, I was actually able to define this line as a function of x. Wasn't that hard. I took the cube root of both sides and I got x or y equals the cube root of x. So I was able to define that as a function of x. But you're not always able to do that. If I had a function like this, and this function was f of y equals y squared minus y minus 2, I can't solve that for x. In other words, even if I say x equals y squared minus y minus 2, I can't solve that for y. So I don't even have a choice when I'm given my function like that. I only can integrate on the y-axis. With the function we were given, where it was equal to y cubed, well, I can solve that relatively easy for y. Y is the cube root of x. So I was able to do it on the x-axis if I chose to. Well, sometimes you can't, and you have to do it on the y-axis. Same with volumes of solids. There's going to be all kinds of problems you're going to get from here on out where you won't have a choice. Sometimes you'll have a choice, but you don't always. Sometimes you have to integrate along the y-axis. And we can see that it's definitely better to do that on certain problems. All right, let's go look at 29. Sketch the region whose area is given by the definite integral, then use a geometric formula to evaluate. A is always greater than 0, R is always greater than 0. Okay? Which one are we doing? 27? So we're doing 3x plus 4dx from 0 to 2. Sketch the region, and then use geometry. They don't want us to use calculus. So let's sketch this line. Where does it begin?
Yeah, 0.
Y equals mx plus b.
Yeah.
So right there it begins at 4.
Yeah, so 0. Yeah.
Has a slope of what?
A slope of 3.
And they want the integral between 0 and 2. So we'll call this point 2, and they want the area of that figure. And they want us to solve it geometrically, by geometry.
So just use geometry to solve that.
What kind of shape is that?
I was going to say we'd break it into a rectangle and a triangle.
We could do that also. It's also a trapezoid. We
Yeah.
could use our information about trapezoids, and I want to do that because trapezoids are important. And there's a trapezoidal method you're going to have to learn. So this trapezoid method is important, but there's nothing wrong with breaking it into a rectangle and a triangle. This point is 4, the area of the rectangle.
8.
The area of the triangle.
The top of that is 2, 6. That goes to 10, right?
Huh?
So then the area of the triangle is 10.
It's the half of the base, which is 2, times the height, which is 6.
Oh, sorry. Yeah, 6. Wow, so it is 6 then.
Area of that is 6. So the area of those two things are 14. And that answers their question. But let's talk about using our knowledge of trapezoids, because that's what this is. That's a trapezoid. We know this is 2. The area of a trapezoid is 1/2 the base 1 plus base 2 times height. This is base 1 and this is base 2. In other words, the bases are always the sides that are parallel.
So in this case, base 1 is 4 and base 2 is 10, right?
Uh-huh.
And then we would have 1/2 base 1 plus base 2 times the height, so that's 14, and then 1/2 is 7 times 2 is 14 again.
14. The key is that base 1 equals f of 0. Base 2 equals f of 2. F of 0 was 4. F of 2 was 10. Remember that concept.
Okay.
Okay? All right. Let's look at 29. Let's graph this. We know that the absolute value function looks like that, only this has a negative sign in front of it, so it's going to be flipped over the x-axis. So it's going to look like this, and then it's vertically shifted by 1. So you move it up from 1 from that point. So here's 1. There's my function. In other words, this represents this function right here. So what's the area under this curve figured geometrically?
A triangle.
And we're going from, yeah, -1, and this point right here has to be 1. And you see how I got those?
Yeah.
In other words, I want to set this thing equal to 0. It's equal to 0 whenever x is -1 or +1.
So that has a base of 2 and a height of 1. So then that's just 1.
For the moment, let's not discuss how we would take the integral of this. There is a way to take the integral of the absolute values, but we're not there yet. They didn't want that. We won't confuse the issue. (31). What kind of function is this?
Isn't that just linear?
It's actually a circle. If you remember the equation for a circle, it's x squared plus y squared equals the radius squared for circles that are at the origin. Well, if you solve this for y, you get y equal plus or minus the square root of r squared minus x squared. So whenever you see something like that, think circle. That's the plus half of a circle of radius 7. So the whole circle would look like that, but this is a plus sign only, not plus or minus. So it's plus only, which means I only have the upper half of that circle. So that's what I have, is the area under that curve is the 1/2 of the area of a circle of radius 7.
So
now, this is a function. Passes the vertical line test. If I create the whole bottom of it, it's no longer a function. A circle is not a function. A semicircle is a function, but a circle is not. And that's perfectly fine with us. We don't need it to be a circle. In fact, it works much better if it is a function, if we can assume that we're dealing with the plus side only of that circle. If we had the full plus and minus, then we would also have the bottom side of it, and we would have a relation, not a function. But this is a function. What's the area of that circle?
the full circle would be 49 pi, right?
So half of it is 24.5 pi. And that's also one that, oh, notice it did go from 7 to 7, minus 7 to 7, which is good, because had they said go from minus 6 to 6, we wouldn't have been able to do this the geometry way. In other words, if you say go from minus 6 to 6 and ask me what's the area of this, I have no idea how to do that with geometry. I can do it with calculus, but I can't do it with geometry. And the point of this part of your homework is do these with the geometry that you know, and you know the geometry for the area of a circle and a semicircle. Okay. 33. Evaluate the integral using the following values. Okay? Well, 33 is evaluate from 4 to 2 x dx. Well, we haven't yet learned that we can just use the reverse power rule and do this, but we have learned that this, I think you've learned it, is equal to the negative of from 2 to 4 of x dx. Have you learned that?
Yes.
Okay. So what is this equal to?
So you just integrate that and then evaluate it, so that's x squared over 2.
No. Do it based on just this information here. In other words, you don't know how to do that yet. I know you do, but you're not supposed to yet. They want you to evaluate 33 based on these 3 statements right here.
So based on those 3 statements, we know that d of x of 2 to 4 is, we know that 6. So we can just put the negative in 6.
You got it. And the minus 6.
Yeah.
What is 34?
34 x cubed using their little chart they've given us that becomes
2 to 2.
2 to 2. So
0.
it was 0?
Always. If you think about it, no matter what curve I have, if I go from one point to another point, what's the area under that curve? 0.
Yeah.
Right? If I go from 2 to 3, well, I got all this area here. But if I go from 2 to 2, there is no area under that point. So when your limits of integration are the same, it's always 0. About 35. Yeah, we're supposed to
35.
do all 5. Yeah.
8x of 2 to 4. So if we know that 2 to 4 is 6, and it has an 8, can we just take 8 times 6 to get the answer to that?
Yes. In other words, you can
Okay,
always
so
pull constants out. Yes. The integral of 8x is equal to 8 times the integral of x. You can pull constants out, but you cannot pull variables out. In other words, the integral of x sine x is not equal to x times the integral of sine. Because x is a variable, you cannot pull it out. Constants you can. So this one would just be this one here times 25, right?
Yeah.
Okay. 37. We have the integral from 2 to 4 of x minus 9 dx.
So if we break that into 2 separate integrals, where we have 2 to 4 of x and then 2 to 4 of 9 dx by dx. And then for the first one, using that chart, we know it's 6. And then for the second one, it's 18, negative 18, minus 18.
Positive 18. So it's 6 minus 18.
Yeah, 6 minus 18.
Equal to minus 12. Okay, let's see. Which one was that? That was 37. We're supposed to do all the odds. So 39. So first thing we're going to do is that. Right? So our first step.
Yeah.
Okay.
First, and then we would, for the first one, we would take half of 60, so we get that to 30. The second one is 6 times 3, so 18. And then the third one turns into 4.
Exactly. 16. Okay, let's see, 41. Given that and that, I tell you what, they don't take any excuse whatsoever to not give you hard. I mean, it doesn't seem like it'd just be easier to go ahead and do these the normal way. I guess they're trying to make a point. So from 0 to 7 of f of x dx would be equal to what?
0 of 7 f of x dx. And we have been given those two, which is sort of 5 and so 0 to 5, it would be equal to the two of those functions up top added together.
Yeah. Like that.
So then we'd get 10 plus 3 is 17.
Correct. Okay, how about b?
And then that's just the opposite of the first one they gave, so we can just go with negative 10.
Okay.
What do we write it?
47. Graph of f consists of line segments and a semicircle. Evaluate each integral using geometry formulas. What is the first one?
0 to negative 2, so that...
0 to 2.
Oh.
A.
Oh.
In other words, we want 0
Yeah,
to 2. We always go, remember these integrands, as long as you got dx's, they're the x-axis measurements.
It looked, on my screen, it looked like a negative 2 due to the integral symbol,
Okay.
but yeah, I blew it up, it looks better now. So, 0 to 2, so that's half of the semicircle.
Okay.
So then, we know that it's a circle that has a radius of 4, so we could just solve for...
Okay, its radius
area
is actually 2. The radius from the center.
Oh yeah, sorry, diameter is 4.
Okay.
So then we just take 2 squared, which is 4, and then 4 pi divided by 4 is pi.
Good. Is it positive or negative? By looking at it.
Negative?
Yeah, all areas under the x-axis are negative. Areas above the x-axis are positive. Okay. B, from 2 to 6.
From 2 to 6, we have a triangle with a base of 1, 2, 4 and a height of 2. So then we just, area is 4.
Yeah.
Since the 2 cancels off the half.
Uh-huh. And C, from -4 to 2, which is this little triangle and that semicircle. The quarter of that semicircle is what? Pi? So that whole semicircle is minus 2 pi.
2 pi. And then that triangle is simply base of 2, height of 1, so that's just an area of 1 added to, or negative 1 added to that. So minus 1.
Minus 2 pi minus 1. From -4 to 6.
4 to 6, that's the whole thing. So then we have the negative 2 pi, we have the negative 1, and we have the positive 4.
Correct. And from -4 to 6 of the absolute value of that function. Now notice, notice what the absolute value looks like. The absolute value of that function looks like the following. In other words, everything that's in negative territory flips over the x-axis so that it's all positive.
It would be the previous answer except for everything's positive?
Correct. So 1 plus 2 pi plus 4. And finally, the area of that function plus 2.
Area of that function plus 2. We would break that into two integrals. So we have the first one, which we already have solved, the f of x, and then the 2x evaluated from 4 to 6, which just becomes 2x evaluated from 4 to 6. We get, or negative 4 to 6.
What's the area of that? We're basically doing a vertical shift by 2 units across the entire from minus 4 to 6. So what is the area of that rectangle that we're shifting everything up by?
The area of the rectangle is 20.
Uh-huh. Exactly. Now, you did it correctly. In other words, you separated it into two integrals, and we already knew the answer to d. So we knew the answer to the first integral. Well, the answer to the second integral is what is the integral of the number 2 from minus 4 to 6. Well, what does that look like? That's a horizontal line at 2. We're going from minus 4 to 6. So that's just a rectangle with a base of 10 and a height of 2. And it's all positive. We also could have done it a little more difficultly, which is by drawing this whole curve, shifting it up by 2. Notice that none of it then becomes in negative territory. It becomes this. So we want this whole area. So it's all positive. So we did it right. We took the area of f of x and we added 20 to it, which has to be the same. I think.
Yeah.
Yes. Yes, it does. Absolutely has to be the same. All right. The next problem, what was that? That was 47. 52. Find possible values of A and B that make the statement true. If possible, use a graph to support there may be more than one correct answer. Find values of A and B that make this true.
A and B that make that true.
In other words, we've got first of all, you can work immediately off of that. What is that? Oops. Yeah, equals what?
That's negative 2 to 7. of f of x.
Negative 2 to 5.
Oh yeah, sorry, it's 5. What did I
This-
get 7?
This one goes from minus 2 to 1. This one goes from 1 to 5. So it's the same thing as the function from negative 2 to 5. And that's the answer. Okay, B. It's a little trickier when you're subtracting.
So the first two we can add together like that, and then for the subtracting, we don't want to lose any off the top, but we want to gain 2 more on the bottom.
Okay, so when we do the
So would
first,
A be negative 2 and B be 0?
so the first two add to this, right?
Yeah.
And then we're subtracting, and you think what? What are A and B?
Negative 2 for A and 0 for B?
Hold on, I'm thinking for a moment. I think it's this. Hold on. See why it has to be that?
Negative.
In other words, treat this like an algebraic equation. A minus B equals C, which means A has to equal B plus C. Well, if I take this and add it to this, I get that. You see that?
I think so. Yeah.
Well, just look at the right side.
Yeah.
If I said this plus this, you can see that the minus 1's the same as that minus 1, so this whole thing has to be the same as minus 3 to 6. In other words, subtraction is just the opposite of addition. So if this minus this equals this, then B plus C has to equal A. And for that to be the case, and I didn't mean these A and B's here, but for that to be the case, A has to be minus 3, B has to be minus 1. Okay? That is less than 0. Well, let's look at our sine curve. As long as it's above the axis, that certainly isn't less than 0.
Yeah.
Where would it be less than 0? What could A and B be?
A is the point. A could be the point where it flips, and then B would be the point right before it comes back.
That's pi.
Well,
that's pi and 2 pi.
but it could be any point along the 2.
You're right.
It could be any point along the 2.
This is just one possible answer.
Yeah.
It could actually be anywhere from there, anywhere from the right of the origin to 2 pi is going to give you a net negative. In other words, the area from 0 to 2 pi is 0. because this is all positive area, this is all negative area, they cancel out. So if we want negative area only, we want just the negative area, or if we added everything but all of that to all of that, we would still get negative. So there's lots of answers for the C part. Let's draw the cosine curve. So what's one possible answer for this?
For sine.
What's this point right there and this point right there?
And then
Pi over 2 to 3 pi over 2 would be completely negative. Once again, we could go from, if we took the whole thing, it's going to be net 0. All this area right here and there adds same as that.
So just any where we cut off a little bit of the positive.
Yeah, any 2 points that don't go all the way from 0 to 2 pi. Cut a little bit off of either end and you have a net negative.
Yeah.
All right. Let's see. 72 is the next one.
72.
X sub 0, okay, the Riemann sum is the sum of the Okay, so the points I'm going to mark off here. This is pi, this is pi over 2, this is 3 pi over 2. They want us to go pi over 4. So the first Riemann rectangle is that one. Actually, the first one is x sub 0 equals 0. So they're using left sums. So actually, let me redraw this. First rectangle is that one with a height of 0. Second rectangle is that one. What's the height of that second rectangle?
The second rectangle.
Yeah, this one right here. What's the height of that?
Like, that's about a half, isn't it?
Well, what specifically is it? It's the sine of pi over 4, right?
Yeah, the sine of which comes out.
Square root of 2 over 2.
Yeah.
Which, you're right, that's about 0.7, a little bit more than a half. Okay, but before we get into that, let's draw this picture out. This is x sub 0, this is x sub 1, this is x sub 2, x sub 3 is, x sub 1 is x over 4, x sub 2 is pi over 3. Back up, I didn't do this right. Here's x over 3, pi over 3, and that is x sub 2. X sub 3 is pi, and x sub 4 is 2 pi. So finding the Riemann sum, where c sub 1 is pi over 6, which is right there. Pi over 6, and that is c sub 1. C sub 2, same thing as x sub 2. C sub 3, 2 pi over 3, right about there. And c sub 4 is 3 pi over 2. So there's c sub 4. Well, they want the Riemann sum. The Riemann sum is going to be f of c sub I times delta x. Back to our definition of this. What you're basically going to do is calculate. We're out of time, and unfortunately I have another appointment I'm going to get to. But to find the Riemann sum of this, just solve that. In other words, the first delta x is the distance from x sub 0 to x sub 1, which in this case is pi over 4. So the first c sub 1 is pi over 6. So we're going to take the sine of pi over 6, that's the height of that rectangle, multiply it by delta x, which is pi over 4. So that's the first part of the sum. That's I equals 1. The next part would be I equaling 2. So the delta x is the distance between x sub 2 minus x sub 1. And we're going to use c sub 2 and evaluate the sine of c sub 2, which is pi over 3. So you get what we're doing?
Yeah, I understand.
Okay. That's probably a pretty good place to end it, and I like that question. That gives me more insight into the harder stuff at the beginning that you guys skipped. The limit. This gives me more insight into the limit definition for integration. All right. Well, I think that was fairly useful. We didn't get to cover all of your sections, but we came close. We covered 4.3, which was good. All right.
Thank you.
Talk to you next Saturday. Go Broncos.
Hope they win.
Talk to you next week, Chase.